Today we will discuss nucleophilic addition reactions. Okay, so let us consider a carbonyl group which is basically say C double bond O, and either you can have two alkyls or have a R which is an alkyl and a H, depending whether it's a ketone or aldehyde. Now, since this bond is polar, as we know, chi of oxygen, that is the electronegativity of oxygen, is greater than the electronegativity of carbon. So oxygen will be having some residual delta negative charge and carbon will be having some residual delta positive charge. So in that sense, we can call this carbon as to be the electrophilic center. Okay. Now the reactivity of this carbonyl group depends on two factors. One is electronic and the second is steric. Okay. So the electronic factor is dependent on the groups attached to the carbon. That is, are they plus I or minus I groups? Okay, so if we have a carbon attached to a group that is showing plus I effect, that means it will push electron towards the carbon, thereby reducing the positive charge on the carbon. So electrophilicity of carbon decreases. Okay, so plus I groups will lower reactivity towards nucleophilic addition reaction, whereas minus I groups will increase reactivity towards nucleophilic addition reaction. Okay, that is what we need to understand. As I said, it is also dependent on another factor, which is factor B, called the steric factor. So this means the bulkiness of groups attached to carbon now, or we can say size of groups. Okay, simpler language, size of groups attached to the carbon. Okay, now large groups lower the nucleophilic addition reaction, and vice versa. Okay, So these are the two factors on which the reactivity of a carbonyl group depends. Another interesting point is, which is related to stereochemistry. Now, the electrophilic carbon is sp2 hybridized. Okay. And so it lies on a trigonal plane. I hope all of you remember your VSCPR concepts. That means what? That if you have, say, this lying in a trigonal plane, groups may come, that is the nucleophile may come from the above, or it may approach the carbon from below. It may approach the carbon from below. Now, just think of a situation wherein you have a carbon and it is attached to two different groups, something like this, or say can be some R prime. Now, if your nucleophile is approaching from the top, and subsequently, say this is H, NuH, so this will open up. Now, what it means, you are adding the negative charge group to the carbon and the positive charge group to the oxygen. So, please understand, oxygen is called 1 and this is called 2. So, this is a nucleophilic addition reaction. This is 1, 2 nucleophilic addition reaction. Later on, we will also study 1, 4 nucleophilic addition reactions. Okay. So that is why we are teaching you this concept. What type of nucleophilic addition it is. Now here, obviously, your carbon, then you have OH. So this is your Nu. I'm just using a flying wedge diagram to make you understand. So say this is coming from top, and that is your stereochemistry. And if it came from below, then we can always say that this is your OH, this is your Nu. So if we have two different groups, obviously the resultant mixture will be having D and L in 50-50 ratio, and obviously the mixture we will say to be as a racemic mixture. So the point of stereochemistry, we can understand that if you have an aldehyde and a nucleophile is reacting with it, we will get a racemic mixture. Or if you have an unsymmetrical ketone, then also that leads to the formation of a as I have shown over here, a racemic mixture. Okay. Now here we have given a question. Obviously these type of questions are asked in competitive exams, and we have to arrange these molecules in the decreasing order of their reactivity. Now if you see, we have two hydrogens over here, so we will judge them on the electronic and on the static point of view. So if you're judging on this electronic point of view, then you see this is having methyl, this is having methyl. There is only one methyl. Here there is no methyl. So methyls will be showing plus I effect. This methyl will show only one plus I effect. So to think from the electronic point of view, this particular carbon will be having more positive charge and followed by this particular carbon, whereas the charge will be very less on this. Okay, so we will say this is the most reactive, followed by this one, and then this one. Again, if you want to judge this from the steric point of view, the size of a hydrogen is very small in comparison to that of a methyl. So where you have two hydrogens, that is sterically less crowded, followed by where there is a one hydrogen and there is a methyl. Okay, the place where there is two methyl, that will be the most sterically crowded. So we can say that the electronic and the factors both are in the same correspondence. Okay, and so in that case also, if you look in those lines also, then the reactivity also is the same. Again, we are given over here, if this is called a formaldehyde, sometimes you need to know the common names. This is a benzaldehyde, and this is a acetophenone. So this is basically a ketone. Okay. One thing that is clear from the above problem, that is aldehydes are more reactive than ketones. Okay, this much is clear. Now, here you have a formaldehyde followed by an aldehyde. So you will think what? See, from here, we know when a benzene is attached to a CHO group, CHO will be exerting a minus I effect, minus M effect. So that means the pi electron density will be pulled towards it, reducing the positive charge on this carbon. So electronically we can say this is having less positive charge than the carbon of formaldehyde. Here also same principle is taking place, and another thing that is taking place is CH3 will be exerting a plus I effect. So there are two factors by which the positive charge on this carbon will be reduced and making it less reactive among all these. So the order will be what? Formaldehyde being the most, followed by that. Okay, now if you judge again only from the electronic point of view, we know chi of fluorine is more than chi of Cl, which is more than chi of Br. So obviously charge on this carbon will be more. Okay, this one will be lesser from the first one, which is even lesser from the second one. So reactivity order is 1, 2, and 3. So this is most reactive, followed by this, then followed by that. Here, it is better to look from the point of view of steric. As we can see, we have two methyls only. So here there is methyl, another methyl, so there is isopropyl group, making it much more bulkier than the first molecule. Here there is a tertiary butyl group, which is even much more bulkier than the second one. So from the steric point of view, we can easily say one is more reactive then 2 followed by 3. Using the same logic, here there is a minus M effect for the problem 6. Nothing is present. Plus I effect is operating over here. And obviously this is a ketone, which will be obviously the less reactive. So obviously the reactivity order is something like that. Now, reactivity towards the carbonyl group also may depend on the size of the nucleophile. Okay, so here we'll be considering some nucleophiles which we will study obviously in this chapter. For instance, if we compare the size of a CN, which is obviously like this, C triple bond N, to that of the size of a bisulfite, which is obviously something like that. What is interesting to note that bisulfite is much more bulkier than that of the CN. Okay, so we will say bulkier nucleophiles react slowly. Okay, so it depends on the size of the nucleophile. Also depends on the basicity of the nucleophile, which you have studied before, that along a period basicity of nucleophiles decrease. Why? Due to increase of electronegativity. So the order for nucleophiles is as follows. For CN, it is most reactive, followed by RNH2, which is followed by ROH. Okay. Now here we have given some examples for addition of such nucleophiles. So the first one that we are considering is obviously addition of HCN, which is followed by hydration. This is basically addition of water to a carbonyl. Addition of alcohol will be producing, we will be studying hemiacetal, acetals, depending on how much of alcohol you are using, from obviously aldehydes, okay, or hemiketals from ketones. So we'll be studying this in detail. Next, we will be studying addition of amines, okay, followed by addition of NH3 and derivatives of NH3, okay, and then we will be studying addition of thiols. Okay, so let's take the first topic, which is obviously addition of HCN. We can also say this is synthesis of cyanohydrin. Now, why that is, I will explain. Just have a look. The general scheme. Suppose I have given you now when I write something inside bracket, this means also that this portion means it is aldehyde. Now, when I write something in bracket, that means if it is not H, then it is R. That means it is ketone. So the reaction is possible for both the aldehyde and ketone. Okay. So now when you are adding HCN, which is hydrocyanic acid. Okay, it leads to the formation of now that becomes sp3 hybridized, and we have a chiral molecule. And both the D and L will be formed here, mind it. DLN are formed. Okay. Mechanistically, what we can think is HCN, which is a weak acid, will lose its proton to a base, forming base and H plus. Along with that, it will relay CN. CN is our nucleophile over here. So CN will now make a nucleophilic attack, and CN O R something like this will be formed, which will now abstract the proton from the base, and it will lead to the formation of OH CN. Something very interesting over here one should note, that these type of compounds are called cyanohydrin because there is a cyano group and obviously OH is there. So for OH we have the word hydrin. Now these compounds are very interesting. Not only they are chiral, if we hydrolyze these compounds in presence of an acid, cyano compounds on acid hydrolysis gives you carboxylate group. So we can think this is a method of preparing alpha hydroxy acids. This is your acid and this carbon is your alpha carbon in respect to the acid. More so, if you treat this compound with NH4Cl, then it will lead to the formation of these are called alpha amino acids. Okay, so that is what it is. Now, one thing one should remember, that cyanohydrin formation in case of ketones are reversible, which hinders its formation. So, keeping that in mind, we should be removing now this one. Okay, so it is better to do with aldehydes only. Okay, next. Now, there's a utility factor about this reaction. It is basically used to separate out carbonyls from a mixture of compounds. Now, suppose you have a mixture of acid and aldehyde. Okay. Also, you can think there is an alcohol. Not a problem. You have a mixture of all this. Okay. Now, only the if you treat this with NaHSO3, only aldehydes form white precipitate, which can be further filtrated and washed, okay, giving you the residue. Mind it, if you treat this particular residue with acid, it gives you back the aldehyde PO form. So this is the use of this reaction. Now, how the reaction happens, we're going to discuss on that. Suppose you have a R, you have a H, double bond O, and you have treated this with Na. This, important to note, a question should be there in everybody's mind, which is the nucleophile over here? Now, let us look at the structure of bisulfite. Is it the oxygen that will react, or is it the sulfur that will react? Now, if you remember nucleophilic factors, then sulfur being more soft, okay, sulfur being more polarizable is a better nucleophile towards carbon than oxygen. In other words, when things are to attached with a carbon, we always look at its polarizability. More polarizabilities, more is its reactivity. So we'll be forming this along with SO3H, but an alkoxide is not as stable as sulfate or sulfite, so there will be a proton exchange or transfer, as you can call it, and the plus charge comes over here. This is your OH, that is your R, this is your H. Now this is your white PPT, which if treated with acid gives you back the aldehyde. Now, some key points. A. All types of aldehydes gives white PPT with NaSHO3. B. Only aliphatic methyl ketones react with this. That means compounds like this will react with bisulfite, but these ones will not react. Again, this particular compound will react with bisulfite, but something like that will not react. Okay. Now we're going to deal with hydration, which is basically addition of water. Now, most of the aldehydes and ketones, okay, they react with water. Mostly the equilibrium lies towards the left hand side, but some portion of the molecules do exist as a geminal diol. However, under certain conditions, the equilibrium will lie only and only towards the right hand side. So we will be knowing what are these conditions. Okay. Now, if we make a comparison of aldehydes and ketones, then we can see from the K equilibrium values itself that for formaldehyde, okay, that for formaldehyde, it is in the order of 2 into 10 to the power 3. For aldehydes, it is around 1.4, whereas for ketones, it is around 2 into 10 to the power minus 3. That is, the reaction is almost lying mostly in the left hand side. For aldehydes, for formaldehyde, it is lying on the right hand side. So formaldehyde will basically exist as geminal diols. They will exist as geminal diols in the water. Okay, a very less amount will be existing for aldehydes, whereas for ketones, the reaction will be lying mostly on the left hand side. Again, here similar factors which we have discussed before. A, electronic and steric decide on which direction the equilibrium will lie. Now, such a phenomenon can be proven by using O18 leveled water. So, if we have, say, acetone taken inside O18 level water, okay, then obviously we will have one OH group. So something like this reaction will happen, and obviously one OH group will be from O18 and another will be from O16. Now just imagine we have got a acetone which has O18 leveling along with the O16 leveling. So this is existing as a mixture with O16 leveled acetone. That means what? That means what? We can say that the if this particular bond broke and that left, we are going backwards. But if you think the reverse, this bond broke and that left, then we are going forward. So since this particular dynamic equilibrium is existing, so we are always ending up with a mixture of acetone having O16 level and O18 level. Okay, if the O18 level of acetone was not formed, then the existence of this would have been in question. But since we are getting, so obviously this is the pathway via which we can say that the O18 leveled acetone is formed. Okay. Now, hydrate, that is geminal diamol formation, okay, is promoted by certain factors. What are they? Option A, electron withdrawing groups. Option B, intramolecular H bonding. Option C, relief of strain. Option D, steric hindrance. Okay, let's take the example of trichloroacetaldehyde. Okay, what is that? Now, if this is undergoing hydration, Okay, if this is undergoing hydration, the equilibrium will lie mostly on the right hand side, because on forming the hydrate, there is a intramolecular hydrogen bonding like this, which is now stabilizing this. This is called chloral hydrate. Let us take another example. This particular compound is called nenhydrine. Just like your trichloroacetaldehyde, this fellow also has electron withdrawing groups. Again, if we create a hydrate, we visualize that there is hydrogen bonding. So such intramolecular hydrogen bonding is stabilizing the geminal diol. Another example which I will ask all of you to try by yourself is this. Okay. Now let us consider the ring strain concept. Suppose you have taken cyclopropanol. We all know this particular carbon is sp2 hybridized, but if you look at this angle, this is like 60. Actually, it should be around 120. What is the difference? Around 60 degrees. So it is highly strained. Now how it can relieve this strain? On addition of water, on addition of water, the sp2 hybridized carbon now changes to sp3. Okay. So now such a relief of strain or change from sp2 to sp3 hybridization is, the strain is released from before. So that particular thing is now stabilizing this hydrate formation. So now if we compare some rings, cyclic ketones, we can say smaller the ring, higher the strain. So more will be its reactivity. So cyclopropanol will be having more reactivity than cyclobutanol, which will be having more reactivity than cyclopentanol. Okay. Reaction of alcohols with carbonyls. What you have to remember over here is when an aldehyde reacts with one equivalent of alcohol, mind it, it is dry HCl, not aqueous HCl. Under aqueous HCl, hemiacetals, acetals, semiketals or ketals, they are not stable, okay? So if you have given one equivalent of alcohol, then you will getting hemiacetal. If the hemiacetal further reacts with another equivalent of alcohol, same reagent, then it is forming acetal. Similarly, ketones, when they react with one equivalent of alcohol, we call hemiketal. If hemiketals react with another equivalent, then it is called ketones. Hemi means half. Okay, just like the word sphere and hemisphere. Okay, so structure wise, what is your acetal? Since you're getting from aldehyde, so say you have aldehyde and we have been given you a ROH in presence of dry HCl. So obviously we are producing OR, OH, H. Again you are reacting with another so this is your hemiacetal. If you have two OR, then it is your acetal. Okay. Similarly, if we have a ketone and we react with ROH, dry HCl, then obviously we will be getting something like this. If we react with ROH, so this is your ketal and this is your hemiketal. So practice problems regarding this and other things we will be doing in the next lecture. Okay.